Clouds. What do you see when you see a cloud? Pretty kitties, rabbit ears, some sea turbulence. Some might see a dragon. That was clouds. What do you see in a cloud? This was in August by Kathy Mimmon. This is called The Rainbow. And this is The Black-Necked Swan by Kathy Mimmon. It's called The Golden Dream by Robert Moline. One more called the Russian Lullaby. Russian Lullaby. This is by Linda Wood. Okay. try the bagpipe jig by Linda Wood. I'm still in the Russian lullaby. I'm playing on what it's called a lever harp. So I have levers that I have to think about here. Okay. Okay. Back to bagpipe jig. I'm going to try a little bit of something I probably know. I have my Kim Robertson book. See, where's Kim Robertson? Oh.
Hi, Kim.
Hi, are we done?
We're just about 30 seconds short of 7:30, so.
Oh, that's fine. I'm all finished because I could have gotten carried away with Kim Robertson.
Well, that's always fun. Thank you so much.
The harpist, you probably know of her music.
Oh, yeah. And I think she may be teaching at Somerset this summer.
Oh, wow. In person?
Usually.
Oh, wow.
Yeah. Sign up for it. Anyway, thank you so much for a half hour of wonderful music. We really appreciate it, and I appreciate the fact you're doing vocals too. That's an added level of complexity.
I don't know. I felt possessed because my hands were getting sweaty in here. So I thought, oh, I'll just Hopefully, you'll enjoy singing.
Yeah, well, it was lovely. Thank you so much. And I think we're probably ready to start the regular program. Thanks again, and we'll see you next month, right?
Thank you so much for having me, and for letting me try this wonderful opportunity.
We really appreciate it.
Thank you.
We ready to change over? Oh, okay. I think that we are on, and so I would like to welcome everybody here to the May 2021 meeting of Orange County Astronomers. Thank you all for joining us. Thanks again, Kim, for a half hour of great harp music. And people have probably been following the news about changing restrictions and all that. We do have a board meeting in a week. I'm sure we're going to be discussing how the changing guidelines may be affecting club activities in the future. But for now, please continue to be careful. Please continue to be safe. Those who haven't gotten vaccinated, I hope you're able to get vaccinated soon, because it sure makes life a whole lot easier. And oh, I guess I should probably introduce myself, shouldn't I? I'm Barbara Toy. I'm the current president. And with that, I think I will turn it over to our announcement crew, which I noticed in the slides was identified as Doug Millar and Company. However, I do believe that we are actually talking Kyle and Ceci and Company. Is that correct, Doug? Okay, so Kyle and Ceci and
here we go.
Wonderful crew, take it away.
Not like we changed it. Oops. Sorry, you get to see like slide 5. Here we go. Here's the beginning. All right, so I think Ceci is going to start off tonight. So go ahead.
Hello and welcome to members. We hope you enjoy this amazing presentation we all put together for you. So luckily we have the board meeting, as Barbara said earlier, May 23rd online. If you want to join us, you're totally welcome to do that. The beginners class is the first Friday of the month. Next one will be on June 4th. And as Paloma was saying, she was saying that everyone should get vaccinated soon. Go ahead, to say that right? Yeah, we should get vaccinated. Like she's getting her vaccine on Friday. Yay, 12-year-olds, you know? And once more people get vaccinated, then we can resume our live events. Looking forward to that. As my mom said, all outreach are currently closed, but after we get our vaccines, we'll be able to resume them.
Yeah. By the way, before the next one goes, anybody who does want to join in on the board meeting, please send an email to Alan Smallbone, because he's hosting that and needs to send you a link. Thank you.
Hello, my name is Galileo, and today the moon is going to be a waxing crescent, and it's going to be a great night to see the moon. Yeah, the stuff is surface.
All right. So the Serious Astronomer, which is the club newsletter, loves articles, images, anything of interest from the club that you would like to share with everyone. So if you have any items of interest that you would like to be put in the Serious Astronomer, please contact Dave Fisher at the email address there, and he will review those items and prepare them to be sent out. Again, these are these guidelines will be reviewed at the next board meeting, as mentioned earlier, about the ANSA site. And then the next general meeting is June 11th. Our featured speaker tonight is from the University of Washington, Dr. Emily Levesque, talking about the last stargazers and the What's Up presentation will be done by Chris Butler from our club. Hope you enjoy. Thank you.
Wow, is it What's Up time?
Yes, Chris,
Really?
the floor is yours.
Wow. Well, you know, I get such stage fright with these things. These meetings are a little bit easier done this way because none of us are wearing any pants. But in future, things will be, you know, a little bit even scarier on stage. I'll get through my stage fright as best I can. Let me go ahead and cue up the slides here, and we will launch into the What's Up. Okay, everybody see my slides? Cool. Let's go ahead and launch right into it. What's going on in the sky this month? Well, first thing, oh, did I pick, there we go. As far as matters with the sun, you may have noticed that we're getting a little bit more sunshine, even more sunshine than Southern California normally gets. That's because we're headed slowly towards summer. The sunset is now 7:45 in the evening. That's the figure for today. So your nights are getting shorter, your days are getting longer. However, we still have plenty of time to go ahead and do some observing. Talking about the moon, of course, we just got a moon report, and yes, indeed, it is a waxing crescent. We had the half-lit moon in the morning sky on May 3rd at the beginning of the month. You may have lost track of the moon for a little while because it's been in the morning sky. We went through the dark of the moon on May 11th. And as you can see tonight, the moon is swinging around to the other side. We're going to have a half-lit moon in the evening sky, the first quarter moon on May 19th. Basically, what this means is for people like me who love the moon, the next week is a solidly good time, convenient time for looking at the moon. We're going to swing around to May 26th, which is the full moon. Something interesting about this, you know, on these diagrams, the way they're done, you'd kind of figure every time we got around to a full moon, the moon would black out when it passed into the Earth's shadow. That doesn't happen in real life because the moon's orbit is tilted about 6 degrees. And so often the moon will miss the Earth's shadow, but not this month. This month, things are lined up such that we are going to have the moon plunged at least to the parts of the Earth's shadow, and that means a lunar eclipse will occur on May 26th. Here's some particulars about this. This is a total lunar eclipse this time, but just barely. A total means going into the deepest, darkest parts of the Earth's shadow, the umbra, as it is known, and in this case, it just grazes it. So we actually only have a total eclipse with the moon at its darkest, that orangish color that you get in a total lunar eclipse, from 4:11 to 4:26 in the morning. That's the only total phase. The others are partial, okay? So if you looked at the moon at 3:20 in the morning, it would be half covered roughly with the Earth's darker shadow. It would still look pretty strange, but not as dark as it would get. If you looked at 5:16 in the morning, the moon would be halfway out of the darkest part of the shadow. From the practical standpoint, this does mean you're going to have to get up early because the eclipse really only starts after about 2:30 in the morning. You're going to start to really notice it. And the moon will be setting in the west. Okay, so you're going to be looking toward the west on the pre-dawn hours of May 26th. And you will see the moon go into the Earth's shadow for a substantial period of time. We see almost all of this eclipse, but not quite. When the moon is finally just emerging from the umbra, I believe it's at 5:52 in the morning, and the moon sets at 5:53. So we're going to see most of the eclipse, but not quite all. Now, if you're not going to be looking at this, you'll see coverage of it later. I know Griffith Observatory is going to have video of the event, and they will live stream it as well if you get up in the morning, but you've got clouds where you are. Now, if Griffith Observatory also has clouds, of course, we won't be able to see it, and that's where space artists like me will create fake images, and you can write into the club and say, what would you like the eclipse to have looked like, and we'll give you whatever you want. as far as the planets, we got a big list, but the first one is the most important. Mercury. I'll often say in these reports, maybe you can catch it at this time or that time. It's not especially a good time. Right now is a good time, a very good time. So it's at what we call elongation. It is about 20 degrees away from the sun in the sky, and it's in the evening sky for once, meaning not getting up in the morning this time. This is just perfect. Mercury is in the evening sky. It's at its widest separation from the sun, so the sun can go down, the sky can start, to get dark, and you can get a pretty good look at it. And the angle that it is to the horizon is actually just about straight up. So it's really a very good time to look at Mercury. If you look 9 degrees below Mercury, you'll see another bright object down there. That's Venus, second item in your list. Venus is bright, but it's still quite low. It's climbing higher though. So week to week, month to month, watch for Venus to be climbing up into the evening sky. Mars is also an evening object for you. It's in central Gemini, but it's not very bright. It's naked eye visible. You can see it, but it's a second-rate star, so to speak. And it is very small, very small. The reason for this is that although we're planet number 3 and it's planet number 4, we're not lapping one another right now. It's on the other side of the racetrack. We're looking past the sun and we see it a long distance away. Notice the size, for those of you who know about astronomical sizes, it's 4.4 arc seconds across. The planet Uranus at the edge of our solar system is 3.8. This is a tiny, little, but bright orange dot in your telescope. You're not going to see detail, but maybe you're thinking about the Perseverance lander, the Ingenuity helicopter, the Chinese lander, which is set to land right about now, actually, on Mars. So it's visible, but it's not rewarding telescopic target. Jupiter and Saturn are in the morning sky. Saturn's up by about 1 o'clock. Jupiter's up by about 2 o'clock. I'll show you a chart where you can find those in the morning sky. Uranus is almost behind the sun. It's just emerging into the morning sky, the pre-dawn morning sky, but it's not well placed for observation at all. Neptune, well, it rises at 3 in the morning in Aquarius. If you're really hardcore into astronomy, you might give that a try, but I'd say wait till a more convenient time when it's up at a better hour. Pluto, well, it's rises about a little after midnight. It's in the eastern part of the constellation Sagittarius. It's at its highest, or transiting, at 5:13 in the morning, just as the sky is getting light. Really not ideal conditions, as if conditions are ever ideal for finding Pluto. So the main thing is Mercury. Pay attention to that. And if you're up in the early morning hours, Jupiter and Saturn. This is a wide angle picture of the sky. At 9 o'clock, and the sky is just fading, the last light of the sunset fading away in the west-northwest. You'll notice Mercury actually appears here in this chart. It's getting ready to go down. You always see Mercury near the horizon like that. Notice also the stars of Gemini have an extra star indicated for you, which is Mars. There are lots of constellations you could look at this time. I'm not going to cover them all. Instead, I'll give you a few specific suggestions, especially for people who are just learning the stars. 4 constellations very high in the sky at 9 o'clock tonight would be constellations like Leo and Virgo. Leo and Virgo are zodiac constellations, so most people have heard of those before. More on that in a moment. Leo is a lion, and it does look like a lion. And as for what he's doing there, he's just lying there. That's standard astronomy joke. Virgo, the harvest maiden, is slightly to the southeast. And Bootes, sorry, I don't have an umlaut in my spell thing, my word processor. I can't put an umlaut on there. It's pronounced Bootes. And Bootes is a herdsman or a bear driver. He's chasing the bear next door, Ursa Major. Ursa Major, the Great Bear, is famous for part of its body being the constellation everybody wants to find. It's actually not a proper constellation. It's called an asterism, or just a star pattern, which is the famous Big Dipper. Let's zoom in a little bit and look at those more closely. We're going to be looking at Leo as our first item. It is marked by the bright star Regulus, one of the brightest nighttime stars that we have. It's in the top 25. Virgo's brightest star is called Spica, and Spica is also in the top 25. Bootes is marked by Arcturus. Arcturus is the fourth brightest of all the nighttime stars, easily the brightest star that's going to be high at this time. Arcturus is also different. You might want to notice, just if you're looking or having binoculars, it's not white. It's not even bluish white like Regulus and Spica. It's definitely a golden amber color. So it's very distinctive. Ursa Major, you can see there the part of its body, which is the Big Dipper. Now there's some other minor constellations, such as next to Bootes, we have Corona Borealis, the northern crown, looks like a little smiley face. Canis Venatici, one of the constellations that is in fact cheating by being composed of two stars. That's not a proper constellation in my opinion. It also doesn't look like a pair of hunting dogs, which is what Canis Venatici is supposed to be. Coma Berenices, the hair of Bernice, I kid you not, is just about straight up at 9 o'clock. That's a hard constellation to see, but there are interesting things in this part of the sky. You might want to poke around if you got a telescope. And then one of my least favorite constellations, and in fact, one I have never drawn lines for in my life, doing about 30 years of these What's Up programs, Leo Minor, the little lion, which is above Leo and is barely visible to anyone under any circumstances ever. I am doubtful that I have ever seen a star in Leo. I'm including it here for fans of cats who just want more cats. There is another lion there, but it's very, very faint. Below Virgo, you may notice Corvus. Corvus is one we're going to talk about a little bit more. But let's start out with a few details, a few things to look at. Look at Leo there. Here's an actual chart of Leo. The blue line is important, and what makes Leo a zodiac constellation. This is the ecliptic. The ecliptic is the path the sun takes around the sky over the course of a year. Those constellations along this path are known as the zodiac, or ring of animals. Zoa for animals, and dies, basically like a dais in Greek, means circle, the circle of animals. This animal does not have it doesn't have the sun in it right now. The zodiac constellations can also be visited by planets. There are no planets in this constellation now, so the lion is unfestered by planets. But you can still see the bright pattern of the stars there. You'll notice in red are marked some little shapes there. Those are galaxies, distant galaxies, and Leo is one of the best constellations for finding them. I know that for me, when I first got a good-sized telescope, finding M65 and M66 galaxies right below the back quarters of the lion, that was a great accomplishment for me to see them. They're little fuzzy patches from the city, true, but it's a big deal to see a distant galaxy. And because of their position right next to that pattern of stars, they're pretty easy to find. Now, there's some other ones there. You see M105, M96, and while we're at it, for fans of the NGC catalog, don't worry, there are hundreds more in this constellation not marked on this map. You could play around in this constellation for a long time. Now, I'm going to show you a picture of M65 and M66 here. Interesting note about this, M65 is at the bottom left. M66 is at the upper left. That pair is visible easily from the city. I'd seen pictures of these before I put a telescope on them. Here, it's actually in Buena Park is where I was looking from. There's another galaxy that's from that NGC catalog, 3628, right next to them. I knew it was right next to them. In this photograph, it should be obvious. You'd swear you'd be able to see it, but the city lights blocked it out. It was just too faint to show in my light polluted skies. So if you really want to see these galaxies, I recommend getting out to a dark sky site. Well, like our own ANZA, when we're able to go back out there, the mountains, place like that, then you'll see these sorts of things. I mentioned Corvus, and I want to put a word in for Corvus. This is down to the south. The big black blob there is the star Spica in Virgo, the maiden. Corvus is right next door. I'm not going to focus on Corvus except to note that it's a small constellation, a distinctive pattern, and can be easily seen, for example, in binoculars, even from the city. Finding this pattern is actually pretty easy. Now, as far as a joke, and I usually try to include one or two, or at least something humorous or weird, Corvus is one of my favorite animals. If you know your Latin, you will know that it is the crow, okay, the crow constellation. And I did a painting of crows just recently for a joke. If you count them carefully in this picture, you will note there are in fact 19 of them. Crows being corvuses, they call them corvids. So this is actually Corvid 19 is the name of this picture. Anyway, that's as far as I go with the humor. Okay, so you can see Corvus there. Virgo is really what we're here to look at, marked by the bright star Spica. This also is a zodiac constellation, and also no planets, no sun, whatever. The moon will pass through this constellation, but it isn't there tonight. The star Porrima is marked, another bright star in the pattern here. If you've got a telescope, I recommend you look at it. Picture to follow in a moment. It's a beautiful double star. There are also marked in red a bunch of galaxies. I'm going to show you a picture of one of them. Longtime visitors to the program will be wondering which galaxy I'm going to show. This whole area is crammed with galaxies. I could show you almost any of them, and I know which one you're expecting. Stand by for that in a moment. But first, Porrima. Porrima is a pair of stars of equal brightness, both yellowish white, and I used to love hunting those down with my dad in the early days of having a telescope. We nicknamed them the headlights. We called them that because for all the world, it looked like a car coming out from some distant celestial highway driving towards you. You develop particular favorites of things to look at in the sky, sometimes by who you looked at them with. My father sadly passed away a number of years ago, but it's a reassuring thing in astronomy for all of us. The stars live a very long time. Porrima is there just as it was in the old days. And so I'll definitely be having a look at it this spring. I promised a galaxy, and here it is, NGC 4697. You weren't expecting that, were you? Well, there are lots of galaxies out there. This is an interesting one, which has been stripped of most of its dust and gas, probably by a collision with another galaxy. But if you look carefully in that soft glow, you'll see a dark band of dust in close to the center of that galaxy. You may not see that in a telescope, but it's fun to know that these are dynamic, interesting places with each with their own unique history. I know you didn't expect me to show you this one because there are other more famous galaxies in this constellation, but no one ever expects NGC 4697 in Virgo. I have to keep you on your toes. Boötes is beautiful and bright, at least as Arcturus and so forth, and it looks like an ice cream cone. It's kind of a nice pattern. I got to admit, there are more exotic things, mostly in this constellation, fainter things as far as telescopic targets. Now, I drop by all the time, but I usually do so to look at something in a neighboring constellation, and I've marked it. M3, the globular star cluster, technically just over the border in Canis Venatici, the hunting dogs. But the easiest way to find it is by looking at the ice cream cone of Boötes and just scooting slightly west from that. As far as things to actually look at in Boötes, you'll see a star almost exactly center screen marked as Izar. It's the second brightest star in the constellation. That and some of the others turn out to be beautiful double stars. Here are some simulations of what they would look like. You see there on the left, Izar is not only a double star, which is pretty enough, but it's a gold and a blue star next to each other. The other star on the other side is called Xi Boötis, And Zyba Otis is a pair of, it's like a golden star with almost an orangish hued star. All double stars are all different from one another. It's a lot of fun to hunt them down. Ursa Major, well, this is a celebrity, of course, with the Big Dipper being included. Lots of galaxies you'll see at the top. One of them's marked M82 and M81. Sure, picture to follow. It's almost obligatory. If you have a telescope, you can hunt those down. Looking along the stars of the Dipper pattern, you see them named Dubhe, Merak, Phecta, Megrez, Alioth, Alcor, and Alcade. The star Alcor and the star Mizar, those are actually even in binoculars. Just for a beginner, if you look at those, you'll see there's actually 2 stars there, and it's even cooler than that, actually. This is the pair you see in a pair of binoculars. But if you look at the brighter star with a telescope, you'll see that it is itself a close pair of stars. You think, wow, there's 3 stars there. Astronomers using sophisticated instruments can see more than we can. There are no less than 7 stars in the Mizar-Alcor system. They really are flying through space together. Just an example of how beautiful multiple star systems really can be. Mizar and Alcor for eyes or binoculars as a wide pair. Have a close look at Mizar if you have a telescope. There's M81 and M82, pair of galaxies, each very distinct and different from one another. This is the sky at 9 o'clock as we just looked at. The Big Dipper pattern just about straight up. The bright star Arcturus, orangish, rising in the east. You can see the lion now that you know what to look for, just at the almost center screen. And then the more scattered pattern of Virgo around the star Spica. But if you give it some time and you're up to get a look at that eclipse at 4 o'clock in the morning, the sky will look like this. Completely different stars. If you look for the Big Dipper, you'll see it's rotated around 90 degrees and is getting ready to set in the northwest. So you have new constellations if you stay up late. Couple things to look for. First, Jupiter and Saturn. I promised you Jupiter and Saturn. Jupiter is brighter than anything else that'll be up at this time. Saturn is one of the brighter objects up at this time. Obviously, if you've got a telescope and Jupiter and Saturn are out, Jupiter and Saturn are probably going to be your star attractions at this hour. For other things to look at, well, there are lots of constellations. We don't have time to talk about them all. I will direct your attention first to the idea of the Milky Way, because if you're in a dark place, you may see this amazing spectacle. If you're in Los Angeles, you will not see this amazing spectacle. Our friends in Canada, the North York Astronomical Society near Ontario, send this picture not only of the summer Milky Way, but if you look at little dashes, those are something else you won't see from Southern California, fireflies in the middle of their strong picture. It's very pretty, isn't it? But if you're out in the desert here or in a dark place, you'll see in the pre-dawn hours the Milky Way. As far as constellations, I do have a couple I want to point out and make sure you see if you get up for the eclipse. Scorpius, I am a Scorpio for what it's worth. I don't believe in that stuff, but it's my favorite constellation. The pattern of the Scorpion is very distinctive. It has a red star at its heart, Antares in the top part, and curves around to a stinger at the bottom. Sagittarius does not look like what it's supposed to be, a Centaur Archer. It looks like a teapot. If I tell you to look for a Centaur Archer, you won't find it. If I tell you to look for the teapot, you'll find it. Both zodiac constellations, get to know them now, because in the summer, they'll be around at a convenient hour. You'll need to know them. Straight overhead, we have 3 constellations, each with a bright star: Cygnus the Swan, Lyra the Harp, essentially, and Aquila the Eagle. Each is marked by a bright star forming a triangle in the sky almost straight overhead, which is imaginatively called the summer triangle. So if you see the summer triangle overhead, the Scorpion in the south, and the Sagittarius teapot, you will have a leg up and be ready for the stars we'll see at 9 p.m. in a month like August. As far as, well, there's your chance to look and see. You see the triangle, Jupiter and Saturn down there, the teapot and the Scorpion. 4 a.m., if you're up, have a look. we're not yet back in the old meeting hall. We've been going there, some of us, for 25, 30, 40 years for me. We don't know exactly, obviously, when we're going to get back to doing this again. And I guess I'll have to put on a pair of pants if I do the What's Up again in the actual lecture hall. I promise I will. But I'm looking forward so much to seeing you all again back in the meetings, as every passing day, every sunrise, every night of stars parading past, getting us closer to doing this again. I'm sure looking forward to it. So in the meantime then, folks, you take care, and thank you very much for your time and attention.
Thank you, Chris. That was wonderful. Enjoyed it thoroughly. Great. So hello, I'm Reza, your Vice President, and I too would like to welcome you to the May 14th, 2021 General Meeting of Orange County Astronomers. I believe we've been holding these meetings long enough that I do not need to go over all the controls again. Let me just dive into introducing our main speaker for the night. Our speaker at this meeting is an astronomy professor at the University of Washington. Her work explores how the most massive stars in the universe evolve and die. She has observed for upwards of 50 nights on many of the planet's largest telescopes on the ground and not. She earned a bachelor's degree in physics from MIT and a PhD in astronomy from the University of Hawaii. Please join me by raising your hand virtually in welcoming Dr. Emily Levesque. Dr. Levesque.
Hi, everyone. Thank you so much for inviting me to speak tonight. I will go ahead and share my screen so we can get started. And what I'll be talking about tonight is the popular science book that I published about 6 months ago titled The Last Stargazers, which is now available anywhere books are sold, and sharing really what this book is about. So this book is an exploration of what it's like behind the scenes to be a professional astronomer and what it's like to work at some of the biggest telescopes and the most remote telescopes on the planet and the sometimes absurd adventures that we have working at these observatories. And as part of writing this book, which was my first popular science book, I got the chance to go to a couple wonderful conferences focused around books, so library conferences or book selling conferences. And at these, people started telling stories about their books or talking about their writing, and they would put a lot of weight and emphasis on the first line of their books. And we can all think of the famous first line of a Shakespearean play or of just a favorite novel that we loved and how it really sets the scene. And it got me thinking, well, okay, what's the first line of my book? It's stories of how we explore the universe. It's adventures of being in some of the most remote parts of the planet. How do I open this book? And I realized the first line of my book is, have you tried turning it off and on again? So it sounds like the start to a phone call with Comcast, but this is actually one of the most frightening things that's ever been said to me at a telescope. And for context, I was asked that, have you tried turning it off and on again, about this? So this is the Subaru Telescope atop Mauna Kea Observatory in Hawaii. And I was observing on it as a grad student at the University of Hawaii. I was 24. I had been granted one precious night on this telescope to observe some very far away galaxies. The night was going really well. And about halfway through the night, one of the computers in the control room suddenly made this like horrible blunk sound. And I looked over at it. And then I looked at the only other person on the mountain with me, who was the telescope operator. And she had kind of frozen in her seat, which wasn't a good sign, and then said, no, it's okay. And she decided to reassure me by saying, I think the mirror is still on the telescope. And I didn't know not being on the telescope was an option, so this didn't help. And I asked her what the alarm had meant. And it was indicating that the mechanical supports holding up the telescope's secondary mirror had failed, which meant that there was effectively nothing holding up that mirror. Now, we had gotten lucky, and the telescope was pointed straight up. So the mirror was being held up by, well, gravity. But to give you a sense of just how drastic this is at a telescope like Subaru, Subaru has a 8.2 meter primary mirror. And for scale, this is me standing underneath the 8.1 meter primary mirror at one of the Gemini telescopes in Chile. So you can see how just epically enormous these mirrors are. So we were hanging another mirror that was still about 400 pounds high above this one in the dome. And the orientation of one of these telescopes, I always like to remind people, is something like this. I use Palomar as a beautiful example of this very classic setup, but the primary mirror will be near the bottom of the screen. The secondary mirror is held up, hopefully, at the top of the screen and suspended high above the telescope to bounce light that's been captured by the primary up to the secondary and then into a camera or something like that. This is how it should work when the telescope is working well. And that alarm suggested that if we tipped the telescope too much, the secondary would slide right off its mount and go plunging down to the concrete floor. If we were lucky, if we were unlucky, it would hit the primary on the way down. So we decided to call the engineering crew and ask what was going on. And they very politely informed us that this was probably just a false alarm. The telescope was probably fine. It was probably just a short in the alarm itself. They had noticed something about that earlier in the day. It would probably be okay. There was way too much probably happening. And I could probably fix it by just power cycling the telescope, turning it off and on again. And it seemed very impolite to say, you know, this isn't a modem. This is a building-sized scientific instrument. I'm not okay with this as a repair tactic. And I was sitting there trying to decide what to do, knowing that if I called it a night and left a telescope that was fine and could be fixed with a modem switch repair, that I was losing really precious time for my thesis. At the same time, I didn't want to power cycle it, be wrong, and then become the grad student that killed Subaru. And I had all these stories cycling through my head from people I knew who had had something go horribly wrong at a telescope. And the one that kept flashing through my mind was this one. So this is Green Bank Observatory in West Virginia and a famous 300-foot radio telescope, which is this immense, you can just see the scale of it, radio dish that one evening went from this to this. And I didn't remember at the time exactly what had happened to that telescope, but I was convinced somebody had tried turning it off and on again. So I was sitting at the Subaru Telescope alone, in charge of the night, trying to decide whether to give up really precious thesis time or risk breaking the largest piece of glass in the world. I had no idea what to do. And this is the story that I decided to open my book with, because it gives readers who are coming to the world of professional astronomy for the first time a glimpse at how our nights sometimes go and what it's like to be the person behind the telescope. And this was the aim of the whole book. If you show people these pictures, if you show the dazzling photos that Hubble takes or the beautiful amateur astronomy photos that we can take, everybody falls in love with the pictures of space and the colorful galaxies and the stars and the nebulae and the ooh-ah side of how beautiful it is. But what not many people know is the stories behind where these pictures come from. And that's pretty understandable because there are 7.5 billion people on the planet, and only about 50,000 of us are professional astronomers. So not knowing what a professional astronomer does is not at all surprising. And when you ask people to picture it, they tend to remember their own astronomy experiences of standing with the telescope in a backyard, and they just imagine it professionalized. They tend to picture a man with a beard for some reason and a white lab coat, unexplained, standing next to a little telescope and kind of looking through it with his eye and taking notes. And again, it's a very understandable picture based on people's hands-on experience with astronomy, but it's very different than how we do our jobs. And I wanted to bring that sort of real world of what astronomy is like to readers of my book. I knew in part that I would have been somebody who would have loved this book as a kid because I knew really early on that I loved space. I have proof. So this is me the year that the Hubble Space Telescope was launched. And I had my little Hubble t-shirt that I was so excited about. My brother describes the grin as, what do you mean 6-year-olds can't use Hubble? But I was convinced that space was fascinating and I loved science, but I had no idea what being a scientist would be like. Where I grew up, there were no professional scientists. Nobody in my family was a scientist. And I just figured science would be cool, but I didn't know what the job was going to entail. Most of what I learned from the movies. And my general understanding from Twister and Jurassic Park was that when you became a scientist, the stuff you studied just chased you a lot. And based on contact, I had just enough of a clue to know that you probably didn't discover aliens every day. So I started college, I majored in physics at MIT, knowing that that was the way to get into astronomy, but was still curious about what exactly the job would be like. And I didn't wind up really getting a close glimpse of this until after my sophomore year, because that was when I went on my first summer research program. And I went out to Arizona. I wound up spending a summer at Lowell Observatory working with a scientist who's still a close colleague today, Dr. Philip Massey. And he took me to Kitt Peak when I first arrived in Arizona for my very first observing run. And we got to the summit. We wandered into the sort of dining hall area for dinner. We sat down and he introduced me to everyone else at the table, saying, "This is Emily. This is her first observing run. We've got 5 nights on one of these telescopes and it's her first time at an observatory." And everyone else at the table got so excited and started saying, "Okay, time when you drink your coffee. Because if you drink it all too early, you'll just crash at 3 a.m. But if you drink it too late, you can't go to sleep. Well, make sure you order your night lunch so that you can eat at 2 a.m. That helps you stay awake." And the advice slowly started turning into stories and things like, "Well, I know a guy who was observing at your telescope and the bathroom door is a little fiddly, so he locked himself in the bathroom during an exposure. And he lost like 15 minutes of time because he got locked in," which is true and got described in his eventual paper. Or there was a woman who was observing and a scorpion crawled up the inside of her pant leg and stung her, which is also true. And then the stories just got wilder and wilder. I know a guy who had a raccoon crawl into his lap. I know somebody who was at a telescope when it got struck by lightning. Did you hear the one about the telescope that got shot? And I was sitting there at dinner with my fork like stuck halfway to my mouth, just going, and I couldn't decide whether I wanted to stay there all night and listen to the stories or whether I wanted to go sprint off to the telescope and start making stories of my own. And I realized later what they were doing in the storytelling, because it's a way of sort of welcoming somebody into a group or into a world, is let me tell you the story of what this is going to be like, and let's start sharing kind of the legends of the field. And it was a wonderful welcome. So years later, this was the sort of welcome I wanted to offer to everybody in my book. It's this behind the scenes view of what life is actually like as a professional astronomer. And it shares these kinds of stories along with the science that's driving them of how we study the universe. I'll put a slide like this back up at the end. If you want to learn more about it, you can go to thelaststargazers.com. It was really just an awesome way to try and share a bit of what our jobs are like with the world. So as part of researching this book, I got to travel all over the world and got to really learn some amazing things and visit some amazing places to hear from my colleagues about aspects of observational astronomy that I didn't have hands-on experience with. I got to visit places like the Gravitational Wave Observatory here in Eastern Washington, which you can see on the upper left with my very stylish hat. I got to visit the Sophia Airborne Observatory, which I'll get to in a little bit. I got the great chance to go visit Palomar and to go back to the summit of Mauna Kea. And the best part of the research was the less exciting looking, but actually quite amazing picture on the lower right, which was my trusty voice recorder. I got the chance to record interviews with more than 100 of my colleagues for this book. And hearing the stories that they had to share, and stories that went back to the first half of the 20th century, sharing some of the most amazing observing stories of the field, was just invaluable. I'm not a trained investigative journalist, so I was learning to interview as I went. And I largely just wanted to get people talking. I learned a lot about how to get people rolling. And I wanted to hear their stories. I wanted to hear their memories of observing, their most adventurous tales, their favorite nights of observing. And I largely let them go. But there were a few questions that I asked everyone. And those are the questions I want to use to sort of frame what I'm telling you tonight. So these are the 3 questions, and I'll start with the first one, which is, what is your most memorable second or third or 10th hand observing story? People were great about telling me stories that had happened to them, but I specifically asked for the story that was absolutely half true, that they'd heard from their advisors, colleagues, roommate, during a cloudy night in an observatory at 3 a.m. when nobody could remember the details, just the stories that had really entered legend status in the field. I wanted to find these stories and see if I could hunt them down and then tell the accurate version, or as close as I could get, in my book. And there were a couple different stories that came up over and over when I asked this question. The first, and the winner by a mile, was, do you have the one about the telescope that got shot? I had so many people ask me this and then tell me some wild version of this story. but this is true. And it happened to the McDonald Observatory 107-inch telescope in Texas. And the backstory behind this is that late one evening in the middle of observations, a gunman went charging into this telescope and pointed a loaded handgun at the telescope operator. Fortunately, no one was hurt in the story, and demanded that the telescope be lowered because he was hell-bent on destroying it. And depending on who you ask, this was a disgruntled grad student at the university, or there was a torrid tale of like spurned relationships on the mountain. It was a disturbed observatory employee who decided that he needed to destroy this telescope. So the operator lowered the telescope so that he could see down the barrel of it to the primary, and he emptied the handgun into the primary. And it sounds tragic, but then you think about the dimensions of this telescope, because the 107-inch primary mirror, 107 inches across, was at the time, with the way we made mirrors, about 1.5 feet thick. And it's made of borosilicate glass, so the glass that's in the Pyrex dish in your kitchen. So take 1.5 foot Pyrex dish, and then imagine shooting a bullet into it. The bullets just kind of went thunk, and they landed in the glass like darts in a dartboard. Nothing happened. It didn't shatter. They just sort of embedded and stopped. So the gunman was underwhelmed. He then started trying to go after it with a hammer, and fortunately at this point he was subdued and taken away. The sheriff was called, and people started sort of looking at the telescope to figure out what had happened. And what the observatory employees realized was that, yeah, the bullets really hadn't done that much damage. They could dig them out, paint them over so that they didn't reflect, and just keep observing. The 107-inch had just become the 106-inch. They'd lost a little collecting area. They still have bullet holes in this mirror today. When they take it out to re-illuminize it and polish it, you can see the holes. So they knew the telescope was fine. The sheriff got up there and took a look down the telescope and saw this and immediately went, "My God, the telescope's destroyed." He was seeing the big hole in the middle that, if you're used to the way telescopes are designed, you know is the Cassegrain hole. It lets the secondary bounce light through to the Cassegrain focus. But the sheriff didn't know this. I guess he thought the gunman was shooting a bazooka and just went, "My God, it's been destroyed." And that is the news that started to get out. This made the national news. Word spread through the astronomy community. This was a new telescope at the time, and people were horrified that it might have been wrecked. So the observatory director at the time, which was a guy named Harlan J. Smith, wound up having to put out an announcement saying, "No, the telescope's fine." And he put it out in the same announcement venue where people usually announced, like, "Hey, there's a new nova somewhere, go check it out," or "This variable star is doing something weird." And then in the middle of all that, there's this announcement reassuring people, "Okay, this happened. The harm suffered from the bullets was extraordinarily small." It's got to be one of the most unusual quotes that's ever showed up in those announcements. And this was the, official record, too, that you could find to track down that this story really happened. So it's a wild ride of a story, but in addition to being a wacky story, there's science in there that somebody new to astronomy will have to learn and understand in order to get the story. You need to know what a telescope operator does. You need to know why we call it the 107-inch telescope. What does that mean? It refers to the size of the primary mirror, which is the most important thing about a telescope. You need to understand the dimensions of that mirror and why the bullets didn't shatter the glass. You need to not make the mistake that the sheriff did and know what the big hole's for. And you need to know what a big deal it is, because how many professional telescopes are there, really? 107 inches, how big is that really? How rare are these? It's just one telescope, how tragic would it be? So to really have somebody understand the story, you need to give them all this background of astronomy and telescopes and how observing works before the story really lands in the way that it should. So this was one of the infamous stories that people kept suggesting. The other one was some variant on this. People would say, there were these weird radio bursts in Australia. We thought it was space and it wound up being something on the ground. What were these things? And everybody half remembered the story, and it was so much fun digging up the full background of what these were. So this story happened at the Parkes Observatory in Australia, which is this big, beautiful radio telescope. And just as a quick reminder, of the electromagnetic spectrum, we are all very used to thinking of astronomy and thinking of light in terms of the visible light that we see with our eyes. But if we go to much longer wavelengths, you wind up looking at radio light. And the long wavelengths mean we design telescopes at a very different scale. We're able to use different building tools, and you get spectacular dishes like the Parkes Observatory. It also means that you're detecting radio light from everything. You detect anything coming at you from far away in space, and you might also detect anything that could be emitting radio emission on the ground. So Parkes, one evening in 2007, detected something really strange. It detected this brief blast of radio waves that seemed to be coming from deep space. And it was unusual. This wasn't a phenomenon that was predicted, and people started getting curious about it. And researchers started saying, we need to study these fast radio bursts, as they wound up being called, to figure out what they're coming from, what produces them. This could be a sort of missing link phenomena in the wider world of quick and brief astronomy events. We should figure out what these are. And an astronomer named Emily Petroff came to Parkes Observatory in the early 2010s, specifically interested in studying these. And she was kind of waved off by people saying, oh, no, that can't have been real. We actually detect these things all the time, and we don't know what they are, but we're pretty sure they're not actually astronomy. We're pretty sure we're getting something from the ground. The team had actually nicknamed these sort of brief blasts of radio light peritons, which is a mythical creature that looks like one thing but is something else. And Emily was convinced that some of these had to be real, but she couldn't study them or learn much about them until she could separate the real from the fake. So she went on this amazing search to figure out what peritons actually were. And in the paper that ultimately got published on these, the entire staff of Parkes Observatory, so everybody that works on the site, folks who work on the cleaning staff and the secretarial staff, were all on the paper because everybody there had to go to work figuring out what was producing this radio interference. And their first clue came when they looked at when the peritons were coming in, and they realized that they were clustering around the lunchtime hour. And space is weird, but it does not care when lunchtime is in Australia. So this was their first hint. And then they looked at the wider area, and they realized, okay, there's several admin buildings on the site. They all have break rooms. Everybody brings in their lunch. Everybody microwaves their lunch. We think these might be coming from the microwaves. So they started doing these really amazing tests. If you read their research paper, some poor soul read the entire manual for a 1970s era microwave. They figured out exactly how they generate possible radio blasts. They practiced, we run them on different power levels for different lengths of time. We always microwaved a ceramic mug of water. They were so careful and scientific about it. But they never made a periton. They ran the microwaves, and it wasn't producing any kind of signal that the telescope would pick up. And what finally occurred to someone was, we're acting like scientists. We're not acting like hungry people microwaving our lunch. Because when you microwave popcorn or dinner, you don't sit there and go, oh yes, we're going to go for exactly 10 seconds. You don't. You watch it count down and you go 3, 2, I'm hungry, it's close enough. And you open the door just before the microwave stops. And when they did that, when they acted like actual hungry people working on site instead of careful scientists, they made a periton. So that had been what was causing these blasts of radio light. It was impatient people opening their microwaves too early. And they went back to the data and they said, great, this explains all of the fast radio bursts except one. That burst from 2007 was not a periton. Now that they knew how to distinguish between these events, that burst was real. And it was one of the starter detections that then led to a whole ongoing field right now, studying fast radio bursts. But it all started by being able to separate these, very mysterious phenomena from impatient microwavers. And I got a lot of variants on stories like this of, that wacky time when we mistook something really pedestrian for something in deep space. And a lot of the stories come from radio observatories just because radio interference is so common. My favorite one that I have gotten goes back to the Green Bank Observatory in West Virginia. This, by the way, is the beautiful new telescope built to replace the one that crumpled that I showed at the start of the talk. And this place is centered in what's called the National Radio Quiet Zone. It's an area in West Virginia where radio emission is purposely kept to a minimum. And in the radius very close to the telescope, if people have microwaves, they're kept in special cages so that they don't produce any excess radio emission. There's no Wi-Fi, there's no cell phones. People don't even drive cars with normal engines. It's all diesel vehicles near the site because the little lightning bolts in spark plugs will create radio interference. They do such a careful job of keeping this site very radio quiet, and it's, as you can see, a beautiful area. And there's a beautiful forest around the area. So they got in trouble once because there was a conservation group working in the forest nearby, and they were studying a population of flying squirrels, and they wanted to understand their behavior and understand their movements. So they gave them all little radio collars and produced the cutest swarm of radio interference sources you can possibly imagine. And to talk to the people at Green Bank, they couldn't observe for months because they just kept getting squirrels. There was no astronomy, only squirrels. And they had to wait for the batteries and the little collars to die before they could go back to doing observing. They basically did engineering work in the meantime while the squirrels cavorted and waited until the collars ran out. And the other area that sometimes surprises people is that you can get false detections in the radio. This can sometimes happen at visible wavelengths too. Even gravitational wave observatories aren't quite free of this. So this is a beautiful aerial shot of the Gravitational Wave Observatory here in Eastern Washington. And the way these observatories work, just briefly, is that you have these two perfectly straight, accounting for the curvature of the Earth straight, arms at a perfect right angle to one another that will reflect laser beams up and down the arms to very heavy mirrors that they use to constantly basically measure the length of the arms. And if there is a slight perturbation in the weighted mirrors that these lasers bounce off of from, say, a gravitational wave passing through the Earth and slightly squeezing and stretching the detector, you get a little signal telling you that a gravitational wave has come by. The challenge with gravitational wave detectors is they are so exquisitely sensitive that they can detect the tiny perturbation of space-time being squeezed and stretched. But that also means they can detect everything else. They detect trucks driving by on the highway. They detect waves hitting the ocean, hitting the shore 200 miles away. They detect rain hitting the ground. And they've painstakingly figured out how to filter out all of this noise. But every once in a while, something does surprise them. They picked up a very odd, sporadic sort of flash of signal causing a tiny vibration in the detector in the middle of a summer here in Washington. And it took them forever to figure out what it was, but they realized that some of the cooling lines that were keeping the equipment of the observatory cold were accumulating ice on a hot day. And there were some really thirsty ravens that were pecking at the ice to get a drink, and their pecking was showing up as a signal in the detector. And the full story of this had this wonderful report written up for LIGO that gave the whole analysis of, we found the ice and we saw some suspiciously bird beak shaped holes in the ice, and then we had a grad student pretend to be a raven and do this and see if we could pick up the signal, and it became a running joke. But even gravitational waves can sometimes get these strange false detections from something as simple as a thirsty bird. So these were the surprising story, or these are the stories that people really love to share of just, we make mistakes when we detect things, and one time a guy shot a telescope. So the second question that I liked to ask was what my colleagues thought would surprise people the most about our jobs. What's the biggest disconnect between what people think professional astronomers do and what we actually do? And I think the most popular answer was we don't look through eyepieces for our day-to-day jobs, that most of our detectors now are very extraordinary cameras that have been carefully built for these telescopes. But the answer that really kept coming up was we have some pretty wacky adventures. I think it's easy for people to think of scientists as, wearing lab coats and just sort of hunkered away in a lab all day, or of astronomers as just sort of nocturnal people who just hide in a telescope. But some of the adventure stories that have come out of people traveling to observatories or chasing the research that they wanted to study have been absolutely amazing. And this is a small sampling of some of the great stories that I either got to experience or hear about as part of my work. And I know that there is a guy in this picture wearing a lab coat and standing next to a little telescope on a tripod. I promise that one's worth it. So the one that I got to experience firsthand was SOFIA. So SOFIA is the Stratospheric Observatory for Infrared Astronomy. It's this amazing 2.7 meter telescope that is built into the back of a specially modified Boeing 747. So this plane can fly up to the stratosphere, so about 45,000 feet higher than commercial airliners, and then open that door in its rear side while it's flying to expose a telescope and then observe. I had heard about airborne astronomy and about SOFIA for years, and I wound up applying to fly on the telescope as a journalist, and then wound up submitting a proposal to use the telescope for my research. It's specifically designed to study mid-infrared light, so light at wavelengths that tend to bounce off the water vapor in our atmosphere. This is why going up to the stratosphere is so good. It clears something like 95% of the Earth's water vapor and is able to detect wavelengths that otherwise we can only get with something like the upcoming James Webb Space Telescope. So amazingly, as part of my research for the book, I got to fly on SOFIA. I was so incredibly excited to get to go. I actually flew on it when it deployed not out of Palmdale, California, where it normally flies out of, but out of Christchurch, New Zealand. And we flew down almost over the Antarctic Circle. We flew close enough to the South Pole that we were able to see the Southern Lights out the telescope. This was the first time I'd ever seen the aurora, and it was one of the most mind-blowing experiences of my life. And I think if you had told the little 6-year-old with the Hubble t-shirt that she'd be, flying over Antarctica in a telescope plane looking at the aurora, she would have been jazzed. She would have smiled even bigger. So that was a pretty amazing adventure to go on as part of studying the book. I also got to interview some folks who told me really great stories. And one chapter of the book focuses on solar eclipses and the astronomers who chase solar eclipses and who have to bring all of their equipment with them in order to study things like the solar corona and the solar winds. One of my colleagues at the University of Hawaii, Shadia Habal, leads a team that calls themselves the Solar Wind Sherpas, and they travel all over the planet chasing total solar eclipses. This is an amazing photo that they took of the eclipse that went over northern Norway in 2015. As part of this trip, she was telling me about her team having to undergo polar bear safety training, which sounds almost like an oxymoron. Polar bear safety training involved firearms and try to not run into any polar bears, is my understanding. But it's not something that you tend to anticipate happening when you think about going into a career as an astronomer. This sort of traveling all over the globe to study the universe was such a wonderful ongoing theme with people that I talked to. Another group that I got to learn about was people who do balloon or rocket-based astronomy. They'll launch enormous weather balloons with payloads of ultraviolet telescopes or gamma ray telescopes attached to them, and they'll launch them from Antarctica or Alice Springs in Australia or Texas or New Mexico here in the US. And their stories of how to engineer and then deal with flying all of your equipment on a balloon and the things that can go wrong were just amazing. I talked to folks who had wintered over at the South Pole to observe at the South Pole Telescope and what it's like to actually spend a winter at Antarctica and the unique advantages of putting a telescope there. So it was this really great map of, how far can we possibly go to use a telescope? And this brings me to the guy in the lower right. So this is George Carruthers, and he is the inventor of the ultraviolet camera. He holds the patent for the ultraviolet imaging chips that we are able to use today to observe ultraviolet light. And he first used his invention in this pretty little looking, at first, telescope. It's about a 4-inch ultraviolet telescope. And the reason it is so incredibly amazing is because this telescope observed from the surface of the moon. It flew to the moon aboard Apollo 16. John Young and Charlie Duke were the astronauts and the telescope operators for a little while. And it took some of our first ultraviolet pictures of the sky, period. We got to observe our own Earth. It got some amazing pictures of Milky Way stars. It's the only telescope that we've ever taken to the moon. When I was writing The Last Stargazers, I had to sort of bracket or limit the stories that I would be telling, or else the book would have been 6 volumes. And I decided I'm going to stick to professional astronomy and I'm going to stick to ground-based astronomy. I'm not going to go into Hubble. I'm not going to go into the space telescopes that we build because they truly are books on their own. And I figured this was fair because the telescope is on some ground. It's just on the moon's ground, but that's absolutely a ground-based telescope. So, had an excuse. So you look at all the different places that astronomy can take you, and you also consider the places themselves and the really remote areas that we go to, and some of the kind of wild encounters with nature that you can have while you're at some of these places. I had people tell me all sorts of stories about the wacky critters that they'd run into at telescopes, the enormous tarantulas in Chile, or the swarms of moths or ladybugs that will like accost telescopes in the southwestern US. The best nature versus telescope story that I got, though, actually came from someone right here in my home state. And it happened at a little observatory in south central Washington state, Manastash Ridge, which is an observatory that the University of Washington runs. And back in the 1980s, this observatory was used by graduate students for some of their thesis research. And a student named Doug Geisler went up to Manastash Ridge one day to start his thesis. It was his first several days of thesis observations. And he had just a wonderful night on his first night. And as any good observer did at the time, he took very careful notes in his night log. So you can see what the night log looks like, and he's noting how many hours did I observe, how many hours were good, how many hours did I lose, what was the sky condition, and getting into things like, the clouds cleared, everything was beautiful, the night went great. He went to bed ready to get up the next day and do it again. And if you notice the date on the observing log, his observing ground was on May 18th, 1980. So when I tell this story, and I saw somebody react, when I tell this story in Washington, everybody immediately goes, because they recognize the date. So he went to sleep after a wonderful run at about 6 a.m, and about halfway through the night, he heard this slightly weird sound. It woke him up a little bit. He thought, well, that was weird, went back to sleep. And he woke up at noon, when you normally do, and realized, okay, I'm going to get up and start my day. I'm going to open the door. And there's always this moment after trying to sleep during the daytime where you head outside and there's this blinding noontime sun, and you go check on the telescope, and then you have breakfast and you get ready. So he opened the door to just blackness. He could not see anything out the door in front of him. He grabbed a flashlight, and the flashlight beam just got swallowed. There was this awful smell in the air, and he was all alone on the mountain. There was no telescope operator. There were no other observers. And he was just standing there going, okay, the world has ended. There's no, cell phone you can check for a news update. He wound up running back inside and fiddling with the radio to see if he could hear some news about impending nuclear war or some other disaster. And it turned out that morning, Mount St. Helens had erupted. And to understand exactly why this looked the way it did at Manastash Ridge, which is pretty far away, you need to look at how Mount St. Helens erupted, because the way this eruption worked was a side of the mountain effectively blew off. And the side that erupted combined with the winds meant that that huge ash plume from the volcano wound up blowing to the northeast. And you can see in the satellite footage of the eruption what happened, because you'll see Mount Helens, that's where Doug was at Manastash Ridge Observatory. That's where the ash plume went. So that's what he opened the door to that morning. And being a good observer, he wrote all this down in the night log. So he knew that he wasn't going to be observing that night. So, hours lost, 6, reason, volcano, sky condition, black and smelly, describes everything that he saw, and then very judiciously goes out and covers the telescope because there's ash settling through the dome, and he knows that the ash can be corrosive. And it has now gone down, this log entry has gone down as just a legend of Pacific Northwest observing. And this is why the 4th chapter of my book, which talks about these sorts of funny encounters between trying to study the universe and being stymied by nature, is titled Hours Lost 6, Reason Volcano. And by the way, you can see the title of chapter 5 in there too, which tells you what that's about. So the last question that I asked people was how astronomy had changed since they began observing. I got the chance to talk to colleagues who had observed for 30 years with older telescope technology, and then for 30 years with the more modern technology. They'd had 60, 70-year observing careers. And I wanted to know what they thought about how the field had changed. And the quickest answer was, the technology is really different. And I had a lot of people who had been observing for decades tell me about observing with photographic plates. So a photographic plate, you can see a picture of what an image from one looks like on the screen, but a photographic plate was this tiny little sheet of glass. I have an example that I can hold up just so you can see how thin these are. There were these thin sheets of glass that would be chemically treated on one side with a silver nitrate emulsion. So when they were exposed to light, the chemical would darken, and you would get this fun little black and white sort of color negative picture of, say, a galaxy. These plates were so hard to work with. They would get delivered from somewhere like Kodak in big boxes, but then they would have to slice the plates down to size so they would fit into the telescope's camera. Astronomers had all kinds of tricks for doing what they called speeding up the plates, treating them chemically so that they would darken faster, because how many little bits of light are really hitting it from a really far away galaxy? So they would bake them or freeze them, or they'd flash them with light, or they'd dunk them in lemon juice. They would use distilled water. One astronomer told me about an observatory that briefly used hydrogen, and working on treating these with hydrogen gas in an area that they nicknamed Hindenburg Hallway. It had special sparkless light switches in it. So they would do all this stuff to the plates, all in the dark, because once you hit them with light, they start to darken. They would take them up to the telescope and load them into the camera, and then have to sit next to that camera all night, usually riding at the telescope's prime focus high above the primary with their plates and the camera all night, while the telescope operator moved the telescope itself, loading plates in and out, shivering. They were just these incredibly physically arduous tools, but they wound up giving you pretty nice looking data. You can see the really pretty galaxy. This is NGC 6946, just in all of its lovely spiral glory. So I got wonderful stories from people of using these plates, but nobody missed it. Everybody was very happy to say, well, and now we get digital data, and now this image doesn't look like this, it looks like this. So this is NGC 6946 now with the Subaru Telescope, the telescope I was using at the start of the talk. And you can just see the exquisite detail that comes out. You can see the dust lanes. You can see the knots of star formation. This is one of my favorite galaxies because it's hosted 11 core collapse supernovae in the past 100 years. And it is just such a mystery as to why so many stars are dying in this galaxy all at once. But you can just see the immediate gain of current technology and what it offers us scientifically. But there was an interesting note alongside this in that the technology is changing, so now our jobs are really changing too, and the job of being a professional stargazer looks very differently than it does in the era when you were, slicing plates and rubbing them in lemon juice and riding next to them alongside them in a telescope. So one of the places that I got to visit for my research was the construction site for the Vera C. Rubin Observatory down in Chile. So it's named after the woman who discovered dark matter. I got to visit early in the construction process. The primary mirror wasn't there yet. They were building the dome. And I got to learn about how this telescope works. And it's this amazing survey telescope that's going to effectively make a movie of the southern sky. It's going to image the southern sky over and over again every few days for a decade. And it's going to give us a decade-long film of anything that's changed in the night sky. If it gets brighter, if it gets dimmer, if it moves like an asteroid, if a supernova appears, if a star suddenly winks out. It's going to see all of this. But the way the telescope is designed is really interesting because it's going to be following a fairly preset pattern. And what that means is that an observer doesn't go to this and control the telescope from night to night and point it wherever they want based on the science questions they're answering. There will be a telescope operator there. There will be one or two other people on site for safety. But when I was there and watching them construct the whole telescope, I remember thinking that they were building a ghost town because it was built to have almost no one there and to operate almost autonomously. And it's amazing how much data the telescope is going to produce, but it's also a very particular type of astronomy where you just need to get a wealth of data and then explore that data afterward. And it was at odds with some of the type of discovery that we can manage in astronomy. And it mostly reminded me of the discovery that I was very lucky to be able to make about 7 or 8 years ago through absolute luck, thanks to sort of observing old school style. So this had to do with a type of star known as a Thorne-Zhitkov object. So these are very strange and very unusual types of stars. They're currently still considered theoretical types of stars. And what they are a red supergiant with a neutron star for a core. So it sounds very strange, but Kip Thorne and Anna Zhitkov back in the 1970s predicted that this was actually a physically stable model for a star. A star could sustain its luminosity and live for a very long time with a neutron degenerate core instead of a normal helium fusing core that you'd see in a regular red supergiant. So here's an animation of how we think these form. So you start off with two massive stars in a binary, and both of these stars are blue supergiants to begin with. Now one of them, the more massive star, is going to die first, And when it dies, it's going to undergo core collapse, and it's going to give us this amazing supernova death. I love that when they animated it, they made the camera shake. And it's going to leave behind a neutron star. Now, when its companion swells up and becomes a red supergiant, it's going to swallow that neutron star. And we actually think that those neutron stars can spiral into the core, disrupt normal core fusion, and then settle at and replace the core. And we think that these Thorne-Jitgov objects could potentially live for a very long time. They might be very short-lived and very unstable, but we should be able to observe them. The kicker is that if you look at this now, the little picture of the Thorne-Jitgov object and the picture of the red supergiant, they don't look that different. It's just a bright red star. And identifying that there's a neutron star in the core is really hard. There's almost no observational signature of it. And the only possible trick is that you will see very slight changes in the chemistry of the star's outer layers, because the presence of that neutron star inside the star will change how the star is producing new elements. So you'll get very strange little excesses of random elements seen at the surface of the star. So Anna Zhitkov knew this, and she emailed Phil Massey and I, that was my advisor who took me on my first observing run to Kitt Peak, and said, we know you study red supergiants. Have you ever thought about looking for Thorne-Jitgov objects? We hadn't, but when she told us about them, we thought they sounded so cool, and we decided we would go looking for them. So we proposed for a couple nights at Las Campanas Observatory in Chile, which is one of my favorite places to go observing. And to observe at Las Campanas at the time, you had to go there in person. That didn't change until COVID-19, when they had to set up remote observing. Until then, you always went to the telescope and actually sat in the control room for your observing run. And you brought along a night plan with you based on the science you had proposed, but you could tinker with it and tweak it. And if it was cloudy over here, you could point the telescope over there. And if you suddenly wanted to add a star at the last minute, you could. And that was what we actually did at Las Campanas. We were trying to collect red supergiants that we had in existing lists that we thought we could have mistakenly classified as red supergiants, but might actually be Thorne-Jitgov objects. And we wanted to measure these stars' chemistry. And at the last minute, as the sun was going down, Phil decided to add just a few more red supergiants to our list. He said, these stars are really red, they're really luminous. We might not know as much about them as some of the other ones on our list, but let's add them. Why not? We have the time. So when we then went through and took our observations, we saw data from these stars coming in real time. And we got to one of the stars that Phil had last minute added to the list. And the data that we get from these telescopes really underwhelms a lot of people. I'll talk to reporters sometimes who will say, hey, do you have some beautiful pictures that you've taken from your telescope? And you'll understand they're expecting Hubble. And they get this. This is what my raw data looked like. So we were using a shell spectrograph, so a instrument that takes the light from a star and separates it out by wavelength and does it in an extremely fine-grained manner. So you can see all those little white streaks going from top to bottom on the screen. That's the light from the star sorted out from reddest to bluest as you go from left to right and top to bottom. Right to left and then top to bottom. And by doing that, we can spot any sort of little dark patch or bright patch coming from a element in the star's atmosphere that's either absorbing light or emitting light. Normally, stars their outer layers just absorb light. You'll have gas in the outer layers of the star that interfere with the light that's moving outward from the star and eventually coming to us. Very rarely will you get elements glowing in a star's atmosphere in this manner. And one thing that one of our colleagues immediately recognized were the bright patches in this picture. One of our colleagues was a woman named Nydia Morel, and she is one of the most experienced observers at Las Campanas. And she was able to look at this raw image coming in, immediately recognize what she was looking at, and then immediately recognize what was strange. And she hit upon these little bright patches, immediately pointed them out and said, I don't know what that is, but I know that I like it. And that was an exciting phrase to hear. That's the best sentence in astronomy and in science. It's never eureka, it's that's weird. And we sort of noted, there's a weird one in here, that's great. And then kept observing and went back and had to process the data and do all sorts of work on it. And months later, when we finished the processing, what we realized was that this particular star had the same strange chemical quirks that you would actually expect from a Thorn-Jacob object. And Nydia had recognized it immediately. She couldn't have possibly known that the weird chemistry was the same chemistry that would come from a TZO, but she knew that something was strange. And she recognized it because we were sitting at the telescope as the data came in. And the star wound up on our list because we were tinkering with our list until the last minute, sitting there as the sun went down and getting ready to plan our observations. So we couldn't possibly have found this star without getting to observe in person and planning our observations by hand. So this is the sort of job that we do less sometimes now in astronomy, because you have a facility like the Rubin Observatory that can do enormous automatic surveys. Now, the University of Washington is one of the founding partners of Rubin Observatory, and I have colleagues who work on it. And one thing I always try to make very clear when chatting with them about this is that what they're doing is brilliant. This is going to absolutely explode the amount of discovery that we can do and the type of astronomy that we can do. And it's so exciting that astronomy is advancing in this manner. I think the amount of citizen science that's going to be made possible by Rubin Observatory, the amount of just sheer discovery that's going to come out of it, and the wealth of data that it produces every night, and the weird stars it's going to earmark that we can then go off and study, like we started our TZO, is going to be amazing. So I can't be more excited about observatories like Rubin Observatory coming into play. But the thing that I like us to remember in astronomy is that we really need all the different tools that we can possibly get our hands on. We need these amazing new survey telescopes like Rubin, and we need telescopes like Magellan that you still go to and sit at and operate by hand. We have amazing historical telescopes like Palomar that are still doing really amazing scientific work, and we need to work across the whole E&M spectrum. Much of what I've been talking about tonight is either radio or visible astronomy. Both of these areas are just vital to the work that we do. And you really want to work across as many wavelengths as you possibly can. So we need all of the tools in our toolbox, and we need all of the different ways to stargaze that are available to us to keep discovering what we can discover as we keep going forward. So just to wrap up, I wanted to share a couple things if folks want to hear more stories like this or more about this type of observing and the people that do it. Back in February, I had a lecture series released with the Great Courses, for those of you who are familiar with, on great heroes and discoveries of astronomy. So it explores the great astronomical discoveries of the past century, and it also tells the stories of the people who made the science possible. And one thing that I love about it is that it plays with the idea of what a scientific hero is. There are infamous names in astronomy like Hubble or Einstein or even somebody like Carl Sagan, who everybody recognizes. But there are so many people whose names we don't know, and there are so many teams that are integral to astronomy. It's very easy for people to think of heroic scientists as like one person alone in a room thinking up theories. And in fact, something like the LIGO Observatory that I showed earlier has needed a team of thousands of people all over the planet in order to do something like discovering gravitational waves. And those 3,000 people are the heroes of LIGO. So this course explores the people and the science behind all these discoveries. And you can find it now either via streaming or on DVD, however you like to watch it. And then finally, I'll put up the information for the Last Stargazers again. Thank you all so much for listening, and I'm happy to answer any questions.
Thank you very much, Dr. Levesque. That was fascinating. I very much enjoyed it. And I see in the audience, a lot of them are showing their praise for your talk. Thank you very much. So the floor is open. Everybody who has a question can use the Q&A option to sending their questions. And you asked to read off them yourselves. But before that, let me begin by asking one myself. And that is, well, the classical view on an astronomer is what you said, like somebody with lab coat looking through the eyepiece, which is not the case nowadays most of the time. Another view, which is more modern one with maybe younger generation, is that astronomers are people who just order images online and the telescope is fully robotic, fully autonomous. And that's not the case most of the time here. So what's the current state? How many of those telescopes are autonomous and how many you still need to go? And what's the future?
So It's interesting. This is something that I explore in the book, sort of the different ways that we can observe, because we've gone from people literally strapped to the telescope with the glass plates to people observing, but now they get to hang out in a nice warm room instead of sitting in the cold dome, to a room that might be dedicated to the telescope but a little bit remote. For example, I did my whole PhD thesis with the Keck telescopes at Mauna Kea. And to use Keck, you don't go all the way to the Mauna Kea summit. You work from sea level, and you're on the Big Island. You can see the telescopes, but the whole operation is set up at sea level and just fiber linked to the mountain. And now we can increasingly operate things remotely. Remote operation has become a huge factor during COVID-19, and my book, I finished writing the book just before the pandemic hit, but that alone changed just how much we can operate from afar. And we are starting to build telescopes that will take in a preset list of programs and just execute it, or telescopes that are even fully robotic. There's really a mix, and the mix is changing. I will say that the robot telescopes are still in the minority, as are the Q-based telescopes, where you sort of say, here's my targets, observe them on a night that's good for you. And I tell stories about both of them in the book. But I do think that still being personally involved with observing in real time is going to have a place for a long time, but we may not be at the telescope all the time when it happens. We may wind up using the remote observing capability, especially more now that telescopes have had to sort of bring that capability up ASAP. All right, so I'm looking at the list of questions. So I love this question, and everybody asks this, and I love having the chance to answer. How did the title "The Last Stargazers" come to be? I've had my colleagues ask this because it sounds like a really depressing title, and it also sounds untrue. We are getting record numbers of, for example, students applying to our PhD program, and there's no shortage of people who want to be stargazers. So there's sort of two perspectives on it. One is that the way we stargaze is changing. We are less going to dark sky sites and sitting at telescopes, and we're more operating them remotely or robotically, like we just talked about. So The Last Stargazers does touch a little bit on an era of astronomy that we're not getting back, and an era that I still think needed its stories written down. But we won't necessarily be going back to plates and prime focus cages anytime soon, so it is a bit of a goodbye to that era. And it's also a point that we don't have to be the last stargazers, that we have solid financial support for research and for science, then we can really build the full suite of telescopes that we need. We can have Rubin Observatory and huge, amazing ground-based telescopes that we operate on a night-to-night basis, and the robotic telescopes and radio telescopes and space telescopes. And by doing that, we can avoid becoming the last stargazers by continuing to support the research. So there's another question. Is there an observatory you haven't visited yet that you would most like to visit or work at, and why? And I sort of have an answer to this, because when I was planning my work for researching this book, I had a list of places that I wanted to get to. And timeline-wise, I was writing this book in my spare time while I was working as a professor at the University of Washington. So I would combine a lot of these trips with, say, going somewhere for a conference and interviewing people while I was there, or taking a trip out to Arizona and hitting a bunch of observatories there at once. And the one observatory where I was just like, you know what, I can't get there. I can't fit it into my schedule. And people tell me so many stories about it that I almost feel like I've been, so I'll just get there later because it'll be there forever. It was Arecibo. And I'm heartbroken that I never got the chance to go to Arecibo while it was operating, because I can't tell you how many stories I got from people about how exquisite that observatory was and how amazing it was to work there, and just the mind-blowing science that it made possible. I'm hoping that the community will start hearing more shortly about plans for what to do with that site, because it really is such an amazing place for radio astronomy, and it's been such a wonderful scientific sort of institution. So we're really hoping there's a way to rebuild or upgrade or do something to keep Arecibo as an observatory, but I'm so sad I didn't get to go there. All right, more questions. Is machine learning being used in astronomy to help discover new things? Yes, I have students who are using machine learning. I have 2 graduate students in my group. Actually, that's not true, because one got her PhD about 3 months ago. But I have 2 current or very recent PhD students who have both used machine learning in their work. If you think about the quantity of data that Rubin Observatory is going to produce. We absolutely need just big data handling techniques to deal with the volume of research we're going to have and the volume of bits that we're going to have on variable stars or asteroids or anything like that. And even among smaller data sets, machine learning really has a wonderful capacity for classification tools or figuring out how we can learn. For example, one of the things that my students was working on, how we can classify stars when we only have limited photometric data, when we only have limited imaging, or we only have imaging in sort of unusual wavelengths. So yeah, it's a great tool for astronomy. Moving to things that are not great tools for astronomy. How do you see Starlink and other massive satellite constellations impacting your research conducted by professional astronomers? Yeah, so Starlink is quite a problem right now. So these are the big suite of satellites being launched. Starlink is SpaceX's satellite constellation. There are other big satellite constellations planned, and they're launching just scads of these little satellites with the intent that you'll eventually have satellite-based internet. And the problem is that they're very bright and reflective, and they're at orbits and at orientations such that they show up as these streaks of bright dots in the sky. You can actually see, I haven't caught them yet, but you can see the string of lights of newly launched Starlinks showing up after sunset and before sunrise as they rise to their orbital height. And telescopes can see them all the time. So I have colleagues that have started to make a habit out of posting their observing photos on Twitter with just the hashtag Starlinked, and you see this beautiful picture and then just this rake of Starlink tracks going through it. And there's been some discussion with SpaceX of how to mitigate this. They've talked about things like giving them little sun shields or painting them black. This hasn't been that effective, and when you're just talking about a company with a financial incentive, it's hard to monetize being good for astronomy. We are happy that they are talking to us, and hopefully we'll be able to have a productive conversation about how to deal with this. But it's alarming a lot of astronomers that people can just launch these satellite constellations and that companies can just launch them and really have a big impact on the night sky, basically regulated by the FCC and not keeping in mind sort of what resources we have to preserve up there. They're also, by the way, really difficult for radio astronomers because they interfere with observing bands in the radio that can really wreck some of the observations that they take, and that does not get fixed with black paint because that's a fundamental aspect of how the satellites operate. So they're for sure a problem. I have colleagues working on it, and happily there are at least conversations happening, so hopefully we'll find a solution. All right. So in my
Emily,
research
can I jump in at some point? I've got a question.
Yeah, absolutely.
I cannot contain myself.
Go ahead.
I've been in this particular club for a long time, since 1984. So I've probably seen about 500 presentations, and there's always a challenge between engaging the first timers and then also satisfying people who are interested in the real science or the technical means of doing these things. And I have to say, in my 37 years, this is my favorite presentation that I've heard of at the OCA. And I think it has so much potential. My degree is in film production. You must nod and say, I'm aware that this can be developed in other ways, correct? Okay, then that's the end. It needs to be, and I'm buying the book tomorrow. Thank you.
I would very much like to talk with you more because I got the chance to write this book. I produced this lecture series with the great courses, and I'm very interested in learning more about screenwriting and TV production because I would love to get more science like this on screen, and I'm in that very dangerous stage for any creative project of I've got an idea without any education whatsoever on how to make it happen. But I would love to learn more about this.
The narrative hook and the capacity of being able to say, I have a story to tell you. You won't believe what happened. Did I ever tell you about the time a telescope got shot? Did I tell you about the time a telescope got hit by a missile like the one in Iraq?
Yes.
That is
or the guy who got struck by lightning while observing, which is also true and in the book. Yes.
Right. A few of these I've heard of. Every one of them is a narrative hook that anybody can get pulled in by. And you can do all your other teaching along the way. This is really sharp, and it'll do a lot of good for your science and the public's appreciation of it. So
And
bravo.
it was the aim of the book, because personal stories resonate with anybody. I got to talk to people who said, I've never been that into science. I've never been that into space, but I loved the movie Hidden Figures, because I got to learn about who these women were and what it was like for them to get into that job and what the job meant to them. And then along the way, those people learned about, orbital mechanics. So the idea of writing a book that drew people in with the human stories, because it's what clicks with all of us and it's what's familiar to all of us. Like, all of us have pulled an all-nighter or understand what it's like to be tired and driving somewhere. And many of the stories that are familiar in the book. Yeah. And then along the way, they wind up learning the science.
It's a right-brained way of learning, and it's a different approach than we usually get. And I would say, in my 30 years of OCA, this is the best talk I've ever heard.
Oh, thank you so much.
But I have to ask,
it's not idle flattery.
Do you know that you have to plug in the Palomar 200-inch to make it work?
I did have someone tell me that.
Do you know why?
I don't remember. They might have told me, but I don't remember.
Okay. They have a ladder that goes up to the Cassegrain focus, and it often got left under the telescope. The guy would go back in the operating room and turn the telescope, and it would destroy a $500 ladder. It was a mobile wheel thing that was pretty big. You'd think you'd be able to miss it. Well, somebody got probably, what's her name that was a telescope operator that we know from OCA? Oh, Helen, we've been in a spa with her a bunch of times. Anyway, she probably designed it. They got a length of 220 volt cord and put a plug in it, and then on the wall over by the operating console from the outside, there's a shorting plug, and not a shorting plug, but a plug, and one leg of that goes to the telescope, and one leg goes to the 220 volt power supply. And if you don't move the ladder over to the edge of the building and plug it in, the scope won't do a thing.
Yep. So one of my favorite sort of you got to plug it in stories is that when people used to observe in the dome where it was really cold, it would get unsustainable to be shivering in a dome for 8, 9, 10 hours. And several different observatories hit upon the same solution of they got surplus World War II flight suits, which had lines run through them. They were electrical suits so that you could actually wear them and be warm, because you can't heat the room. You get the atmospheric turbulence that makes observing terrible, but you can heat the astronomer. And the only catch was you had to plug them in. And some of them could be plugged into like a battery, but some of them would get plugged into the wall, at least if you had the right plug for it. And there were several telescope operators who told stories of, kind of having to chase down astronomers because they'd be wearing the suit, they'd be working, they'd get excited, they'd forget they were plugged in and run off across the floor and just like unplug themselves and be dangling wires behind them. So yeah. The fewer moving parts and the fewer wires, the better, is my impression.
Oh, no kidding.
Yeah. Sorry, go ahead. I don't know how much longer. Oh, sorry, Doug, I think you're muted. I don't know how much longer we have, but I'm happy to keep answering questions.
Let's cover the question from the audience and then we'll discuss it. Thank you.
Yeah, I'll do a couple more, because a couple folks are asking about the Thornjitgov object mergers and how long it takes them to merge, or what happens when they merge. Why doesn't the red giant just collapse around the neutron star and make a black hole, or how long does it take them to merge? We actually don't have very sophisticated simulations of the merger itself. When Kip Thorne and Anna Zhitkov predicted them, they were doing a study kind of from the inside out, saying, could a star even stay stable if it was supported by neutron degeneracy and quantum physics instead of the thermonuclear fusion energy released when a star is fusing something in its core? And the formation work came later. And there were a couple different ideas that a red supergiant could swallow its companion. There's one I love where you have a red supergiant and a star in a binary. One star dies as a supernova, and a supernova is almost never symmetrical, so the star gets a little kick, and the neutron star gets like kicked straight into the red supergiant, which I love because it means the supernova has great aim. But what we haven't really modeled, at least with modern tools, is the spiral in and the amount of time it takes. We've been able to look at the chemical consequences of it and what it does to the fusion in the core, but we haven't done, the exact time of the merger. One thing that we have done is we've looked at what gravitational wave signal Thornjitgov objects should make, because the collision of the core and the neutron star should create a little burst of gravitational waves, and a TZO, while it's spinning, should actually generate a gravitational wave, period, because you have a slightly asymmetric neutron star spinning and spinning and sending these little density waves in space-time out in every direction around it. So I actually just had a paper published with a research student at Northwestern where we were modeling what the gravitational wave from a Thorne-Ship-Gov object would look like. And what's great about that is it would be direct evidence that there's a neutron star in there. Right now, we've got weird chemistry, which is neat, but you could explain it in some other way. A Thorne-Ship-Gov object becomes the most satisfactory explanation, but it's never perfect. And actually detecting the neutron star in there could be done with gravitational waves. So that collision, like, I'm glad people ask questions on it because it's a really intriguing aspect of how these stars work. And then, so there's two questions that I want to touch on. Does my book touch on amateur astronomers, like variable star observers and their contribution? It does not, beyond mentioning that they're fabulous, simply because, again, I had to constrain the coverage of the book, and I think a whole book could be written about AAVSO and about how amateur astronomy has become such a valuable part of the community. I mean, I have students dealing with AAVSO data and working with it to study things like luminous blue variables and how they work. So it does not, but I hope someone writes that book because it's a really cool aspect of astronomy. And then someone asked about the TMT, so the 30-meter telescope currently slated to be built on Mauna Kea. I'm afraid I don't know much about what the latest news on the TMT is. I know that it is an ongoing process, but I do write about it in the book. And it's an aspect of astronomy that I think would surprise a lot of people and that also isn't unique to the TMT, which is controversy around telescopes and controversy around where they're built and where the controversy comes from. I was at the University of Hawaii when the decision was made to build the TMT at Mauna Kea, and I was not there by the time there was substantial pushback, but I think most of the astronomy community has seen this in one way or another. There's a wide variety of opinions. There's a very high tenor of emotion around it. And I wanted to put that in the book along with examples of when this had happened previously. There was a telescope in Arizona built on Mount Graham that was deeply controversial when it was being built for precisely the same series of reasons that have come up with Mauna Kea. And I think somebody not familiar with astronomy would look at that and go, why are people mad about a telescope? How could a telescope upset anybody? And it's a much more complicated story than people are mad at a telescope that I wanted to make sure got told. So there's a chapter in the book that delves into the TMT and Mount Graham and why this is a debate. And I think hopefully emphasizing that it is not a simple debate, but that it's one that is ongoing and should be understood. All right, looking at the other questions. Somebody asked about me getting into MIT. I'm afraid I don't remember how that wound up working out, except that I remember getting my acceptance letter and being extraordinarily excited about it, which is actually a story I do put in the book, because the book very roughly follows sort of my trajectory of how I entered astronomy and how I learned about this world as somebody who didn't have scientists in the family, who didn't know any scientists growing up, and sort of learning what this world was like. I figured that that would be a good entry for readers as well, but it was an absolutely wonderful 4 years. I was so happy that I got the chance to go to MIT, and it really did. It is where I wound up learning what being a scientist was like and what working as a scientist every day was like, and how I got convinced that that was for sure the job for me. And then the very last one, can two supernovas merge? That's a great question. When I imagine something like two supernovae merging, what I imagine is two massive stars very close to one another and at very similar points in their lives, which shouldn't be quite as strange as it sounds. It's not that unusual that you might have a binary system of two stars of a very similar mass. And if one ignites as a supernova, there's a shockwave that's going to pass through the companion. Now that shockwave is going to pass through the whole star, so it will squeeze something like the star's core. It'll raise its temperature, it'll raise its pressure, it'll change the density. And that could, in theory, be enough to propel the star into a different evolutionary state. I'm not sure that it would quite cause a supernova, though, because a supernova actually starts as a collapse. It happens when a star eventually starts making iron in its core iron can't be fused, so you can't be fused without taking energy, so you can't use iron fusion to support the star, and eventually the gravitational press of the star wins and the whole thing collapses, bounces off itself, and we get the bang of the supernova. So I'm not sure one supernova could trigger another, or that two would necessarily happen simultaneously, but you could see one supernova do very weird things to a companion. We've seen, we think, examples of stars that were in a binary with a star that died as a supernova that are now being ejected out into space, or stars that have got really strangely chemically polluted by a companion that exploded. That's actually been an alternate explanation proposed for our Thorn-Jitgov objects, that their weird chemistry could be that another star died really near it and just polluted the surface of the star with the supernova products, which we don't think is the case, but would still be really cool if it was true. But yeah, it's a fun question to think about. And I think that's all the Q&A questions.
Excellent. Thank you very much again, Dr. Levesque. That was fabulous. And thanks all the attendees for staying with us till the end. And thanks for all your good questions. So I hope, please check our calendar on the website for all upcoming events at ocaastronomers.org. And with this, I would like to thank everybody for joining us and wish you great times ahead. Bye.